Hello everyone, it is Tuesday, October 3rd, 2023, and we're here back to do some live coding. Welcome if you're out there or if you're not. We're doing this for fun, so I hope you're here for fun. And yeah, and I can hear my voice repeating. Okay, I'm gonna mute that. So as the title may suggest, we are going to learn about Pytorch tonight. Apologize about scheduling this for Sunday and then pushing it back, but you know, we're doing it now. It's better than never. I got some requests last time that I was streaming that people wanted to learn how to use Pytorch or how to train some deep learning models. And we don't do that much of that on stream, mainly because it's kind of hard to do and explain as you're doing, because some of it's really slow. When you're training a Pytorch model or a deep learning model, it does take some time. But I have recorded a YouTube video that I'm almost done editing and I'm going to release about how to get started with Pytorch. And I tried to make it more easy and approachable for those of you who just want to learn how to train models. And I figured we could do a live stream to talk about it before I release that video. What do you guys think? My grandson will watch this live. Someone says. Gabriel says, good afternoon. Let's go. Jeff is here. We got a good crew here. So thanks everyone for joining. Shall we switch over to looking at... Yeah, let's look over just at my desktop like this. Okay, so you guys can see this. There we got the chat there. By the way, if you're not watching on Twitch, you should. I just changed my Twitch name. So if you go to my old name, it's going to be gone. I just changed my Twitch name about 30 minutes ago to Rob Codes Live. I didn't want to overthink it, so I just picked the first thing that came to my mind. And, you know, it's a decent name for what we do here on this stream. So if you aren't on there yet, please join. I'm going to put the link here. And then you can do cool things like text to speech. If someone is on the Twitch and they want to test text to speech, please go ahead and give it a try. Let me go to Stream Manager. There we go. And we got one follower. All right. So we are going to learn about Pytorch. Let's see what you guys were saying, though. I saw something there. Tensors are like Numpy arrays, but better. In my opinion, people shouldn't even learn Numpy. Well, that's an extreme take. Just learn how to interact with tensors. Why learn 2 Python libraries when you can just learn 1? Debate. Okay. Ayahusaka, I hope I said your name right. That's a good point. I mean, Pytorch is very similar to Numpy. I think Numpy is still here to stay. I can't really tell you exactly why Numpy is superior to Pytorch, but anytime I use Pytorch, it's typically because I'm going to train something on a GPU. Now, like you said, import NumPy as NP. And let's import Torch. Now, I don't think I have Pytorch installed in this kind of environment, which is a good thing because then we can learn how to do it ourselves. So let's do Pytorch install. And we're going to read about how to install Pytorch locally. I'm going to go over to my terminal here and make a new window. And I'm going to activate my Kaggle content environment, which I created recently to be like my 2023 Kaggle environment. Let's install Pytorch stable version 2. I'm on Linux using pip. And let's do NVIDIA SMI so I can just see, oh, that's too big, that I am running I do have my GPUs with CUDA installed on this machine, and CUDA version is 12.2. So, oh, they don't have 12.2 supported. This may get interesting. Maybe that's why I had CUDA 118 before. Oof. 12.2 support. Maybe I have to use the nightly build. Yeah. So if I use the nightly build, I can install it for CUDA 20.1. This is why you don't try to be in the bleeding edge of drivers, but it is what it is. I'm going to see if I can download this. Oh, it's like 2 gigs. Let's see if in my 2023, this is my old one, if I can still import Numpy and import Torch. All right, so I think this is an older version of Torch. And I want to see if, let's check if a GPU is available using Torch. And we do that by using torch.cuda.isAvailable. And it says true. So even though in this environment, I'm installing the newer version of Torch, it still works with my old drivers here. I don't know if I do NVIDIA SMI here, it does say I have CUDA version 12.2. So we're just going to roll with it as long as that works. And now let's just look at So yeah, let's look at Numpy. And compare it to Pytorch. Pytorch advantage is evident on the GPU side. Yes, yes. I love it. I'm here to learn, perhaps also implement hand sign language CNN. Cool. You're in the right spot. All right. So basically Numpy and in some ways Pytorch allows you to work with arrays. And we're talking about arrays that are vectors of numbers. So why isn't this working? All right, so if we do np.ones and we do 4x4, what this is going to give us is a two-dimensional array that is in this shape of 4x4, and all the values inside of it are ones. We can also do things with NumPy, like use random and make like a random array, which is 4x4. So all this is each value is a number. Each element in this array is a number, and they are organized in a fashion that they have relationships to each other. Like there's one array that is parallel with this other array, and they're stacked into this 4x4 dimension. Now, the crazy thing is you can get more than just 2 dimensions. So now we have a 3-dimensional array. If we do 4x4x4, and you could think of this like if we do 3x3x3, like a Rubik's Cube. Like now we have numbers that are in 3 dimensions where you kind of have each square of a Rubik's Cube and a number representing that. Now, what makes Torch good? Well, Torch can actually do a lot of the same stuff. In Pytorch, you could do ones just like we did before. I think the syntax is slightly different. So we do like this. And now we have, instead of a NumPy array, we have a Torch tensor. right? And this torch tensor is of shape 4 by 4, or we could make it 4 by 4 by 4, and it's 3-dimensional. Now, I didn't mention this before, but we could also make this, like, there's no limit on the dimensions, and we could make it 4-dimensional, 5-dimensional. It kind of doesn't make sense, like, conceptually in our brains, because we can't think of like a 4-dimensional object. But you could think of it, at least in terms of 4 dimensions, like if we did have a Rubik's Cube, which is 3 dimensions. But then we also have one axis, which represents time. So if we have a Rubik's Cube, you think of these first 3 dimensions. And then this last dimension maybe is 128. That could be number of steps in a sequence of turns to that Rubik's Cube, right? Or let's say we made that the first dimension. So then we have, so now we're starting to think about things in terms of torch arrays or NumPy arrays in terms of each dimension representing something. So let's just say that the first one in this is time, and then it would be like x-axis, y-axis, z-axis. So then if we took this NumPy array, we call it Rubik's, and we took 0, the first element in the time dimension, now we just have one Rubik's Cube, which is these 3 by 3 tensors, right? Similarly, we could take all the time dimensions and just take the value in the 0 dimension of the cube. If we're thinking about this as a 3D representation of a Rubik's Cube, this 0 dimension across all the time by doing it like this. Now, Torch also can do a lot of other things, like we can do random numbers like we did before. That works just the same. You can do, indexing like I just showed. What if we have like Rubik's Cube 1 and Rubik's Cube 2 that look like this, and we would print Cube 1 and Cube 2 just so we can sort of see what they look like. It's trying to scrunch it all in here. But we can actually add these together. And it will broadcast the addition or subtraction if we do it this way. So this top left number has taken, I actually think it starts here. So this is the second top left. So adding these two numbers makes 1.78. And it just, when we added these two together, we actually added each index value with the other index value of our second array. This is the same thing that we could have done with NumPy. So we could have done like NumPy random. And this needs to be in like this. Right? Cube 2. Now we can add these together. The numbers are different, but you get the point. Like the same idea, principle with arrays of and linear algebra that you can do with NumPy, you can do with Pytorch. Now here's the difference. If we have a NumPy array, three by three. I don't know why I called these Rubik's Cubes when they're actually 4 by 4 here. I guess 4 by 4, if you do Rubik's Cubes, some people do 4x4s. But the difference is with Numpy arrays, this is always on our CPU, right? Hello from Mexico. Raul, welcome. Thanks for hanging out. So this Numpy array is always sitting on our CPU. And if you know anything about how computers work, I'm just going to show you here. This is... No, wait. I'll show you HTOP so we could see. This is my computer running right now. These are all the processes running on my computer. The important parts of your computer are the amount of memory that you have. So that's the amount of data that's in a location of your computer, which can be quickly accessed. So your computer can quickly access this data and it will load it from your hard drive to memory and just let it sit in there if it's using it. So my OBS is using memory right now. Chrome is using memory. And also my Python, my Numpy array right here is sitting in my computer's memory. It's also when all these multiplications and additions are being applied to this. This is a very small example, but the CPUs, so these are all the cores on my local machine's processor, are the ones that are doing the heavy lifting for moving the data around and actually doing the operations, right? Now, CPUs are really good for doing these types of operations, especially when they're more complicated. Like more than just addition or multiplication, CPUs can efficiently do a lot of operations that most software is written for, and it's optimized and compiled to work really well with stuff like your operating system. But in certain situations, it actually is... Oh, what was that question? Where's the chat? Is there a Twitch chat that I'm not seeing? Do you have 64 cores? Yes, I do. Oh, wait, man. For some reason, my Twitch chat hasn't been here. I thought Twitch has just been really, really quiet. Ah! Pop out chat. Now I have Twitch here. LMAO, he lost us. Of course you're missing Twitch. I know, Imposter Engineer. I apologize. So where were we? We were talking about how Numpy, everything's sitting in my computer's memory, and CPUs are really good for doing certain type of operations. And yes, my computer has 32 cores and 64 threads. But why would we want to use a GPU? Well, GPUs are really good when you're trying to do these type of simple operations, but at scale, like on very large arrays, and you want to do it over and over and over again. And that's exactly the situation you find yourself in when you're training a deep learning model, because you want to perform, to calculate these gradients and then update the weights in a model. And you want to do it over and over iteratively. And GPUs just are perfectly designed for this. They're designed originally to run graphics, but it so happens that they're also really good at doing this for stuff like deep learning and for, I don't know, Bitcoin mining. Ignored. What? Who is ignored? Chuckling Kizim. I see you now. Hey, Rob, Youssef says. Hey. Hey, so who used the text to speech? I think I heard it. Did you guys hear it? All right, so with a torch array, if we did torch rand and make a 3x3 random array, if I do dot device, I actually see what device that this array is sitting on, and it's currently on my CPU. But I can say to CUDA, and let's be explicit and make it my first GPU. Now, testing comment. You're on. It works. So with this torch array, originally, if I did device, it's on my CPU, but I can actually move it over to my GPU. Now, if I want to make a second torch array and add it to the first one, just like we did before, what do you guys think is gonna happen? Say in chat what you think's gonna happen when I try to add these two torch arrays. I made the first one. Let's just put this all together. I made the first one. I moved it to my GPU. And then I made a second one. And then we're going to try to add them together. What do you guys think is going to happen? Can you send the array to your keyboard? Oh, I forgot my keyboard's on screen. Take a wild guess, people. Matrix Edition. I think you can hear, but we can't. Oh, you can't hear. Man. Yeah, I thought I had the text-to-speech working the other day. Explosion. So, XKKKMMMSI, you were right. It's going to give us an error. And the reason why it gives us an error is because it needs the two arrays to be on the same device. But it notices that this first one is on, if I do, this first one is on my GPU, on my first GPU. And the second one is on my CPU. Now, how would I fix this? How would I fix this? So both should be on the GPU. Yeah, so I fix this by just taking the second one and putting it on my GPU. Now if I add them, there it goes. They add. And I actually don't know if I do this, if I add these together and I use time it just to time it. 6.8 microseconds. And then if I do the same thing, I don't think it's actually going to be any difference in speed. But if I do the same thing with these devices on CPU, yeah, so it's actually faster just to do this on CPU. It's not a very fair comparison, but you'll see when we run things, when we actually start training a model, it's much faster to do things on your GPU because it can parallelize these operations that it's doing. All right, so that's like a brief intro to how we interact with tensors in TensorFlow. But we want to actually train a model, right? So I have an example here that we're going to go through. And to start it, we need to actually get some data. And we're going to use this data set that's not that large, but it's a data set of cards. I'm going to copy the command line interface What? Why isn't it? All right. All right, so I'm going to download this data set. It's about 385 megabytes. It's not very large. And I will share it with all of you. Big arrays are faster on GPU, maybe. Yeah, it's really shown at scale. So it's hard. It wasn't a fair example for me to show you guys, but I did want to just show you that the time difference is different on this. And we'll actually try to train a model using the CPU first, and I'll show you how slow it is. All right, so this data has downloaded, and I'm going to unzip it. Actually, let's make a directory and move it. And then in here, we can unzip. Lots of images. All right, so now if I open up this folder, you guys can see there's some models. There's a CSV, but mainly what we're trying to look at here is our training data set. And if I look in the training folder, there are different folders for each of the cards. So if I go to Queen of Diamonds and I click on it, I see here is an image of a Queen of Diamonds. If I click over here, different kind of one. They're all different, but they're similar enough that we should be able to train a classifier to be able to identify like that this is 7 of diamonds. Right? So we have a folder. In each folder are each of these 53 different cards because we also have jokers. Let's see if it has jokers. Yep. And let's see how we would interact with this. Okay, so the first thing to keep in mind is that we would want, when we want to interact with any data or train any sort of model, oh man. We need to make sure that our, we have a data loader and that we've written the code that handles pulling these images from our computer's hard drive and formulating them into Pytorch tensors. So just in a second here, I'm going to show you how we're going to do that. All right. So luckily, Pytorch has some really nice built-in classes for doing this. And we can go into the utils data and we can import a data set and a data loader. So what we're going to create here is a card data set, which will take in one of these images every time we load it. Let's make sure people are following. Where is my show pop out? Here it is. Any questions? All right, so we have a data set, and then we're actually going to take the data set and wrap it with the data loader. But let's start with making our data set. And this is pretty much what you do most of the time when you start a project with Pytorch is creating your data set. So let's call it a plain card data set. We'll create a class that's called plain card data set, and it's going to inherit from Pytorch's base data set. Okay. So when we create this class, we could make a data set from that class. This class just allows us to create an instance of it, but this instance is inheriting from Pytorch's data set. Now in most classes, you're going to first define an init. This is basically how you set up your object, like the required things to provide this class when you create it initially. So we're going to say it requires this data directory to be fed in, and then we'll make a class variable called datadir. So you always need this init with any class. The other two methods that are required when creating a Pytorch dataset are length, len for the length of the object, and this we'll create later. This will allow our dataset to have a length. So if we were to run len our data set, this is what it will return. And then we also need to define something called get item. And this will actually take an index. It always takes an index. And what it will do, it will return the item from the data set for the provided index. And it can return it as a Numpy array, but we'll have it return as a Pytorch tensor. And this item could really be of any shape, but typically for the training data set, it will return the image in this case, and then the class that we're trying to define. So we're going to return a tuple of the image and class. Got it? LOL tit. What is provided in the inheritance from the Pytorch dataset? Good question. A lot of stuff that we're going to see here, especially when we wrap it with the data loader. But all you need to know now is that the main things are you're going to initialize it, make sure that you have whatever you want to feed in. Like you could actually feed in a pandas data frame that has all the locations of the files, but we're going to do it a different way. Then you need to make sure that you have something that can return the length. And then you need to want to create this get item portion that will pull that whatever index you give it. So this should be able to handle an index from 0 to whatever the length of your data set is. So I'm actually going to cheat a little bit here. Okay, so I'm also going to add this. It's a transform. This is pretty typical when working with image data because you're going to actually have to manipulate the image some when it comes into the data set. So we're going to give it a transform. And then we're going to use from Torch Vision this little helper, which is this image folder data set. It kind of makes all this stuff that we're doing unnecessary, but I think it's useful for us because of what we're doing. We're just trying to explain how this data set works. But what this allows us to do is provide just a folder where a bunch of images are, and then it's going to handle converting this into the image as an array and the target, which is going to be one of those classes that whatever folders it's in. So it knows to look at the folder structure and then create the label based on that folder structure. So you can imagine this is helpful if you had a bunch of images and you want to classify them. All you got to do is drag and drop them to two different folders, right? Okay, so we have our image folder. Now all we have to do when we're returning this length is actually return the length of this self.data. And then for get item, we just need to return self.data and then the index location. Now I'm also going to add this other thing which will make it easier for us to identify what the class numbers represent. But you can ignore this part. All right, so let's try to create our data set. What do you guys think will happen if I try to run this next cell of code? What will happen? We're going to create an instance of this playing card data set. Any guesses? What is self.data? Self.data, okay, so with the class, anything that starts with self, within this class, we can then reference anywhere else in the class. So we've defined self.data here as an image folder with the given data directory and the transform that we're providing it. This is and then this kind of getting at my next question. So you think that you're going to load the folder? I don't know. You guys have any ideas what's going to happen? Yeah, it's going to complain because it needs the directory. Good point. So when we initialize this, we have to provide it our data directory, which let's define this. We know that it's, wait, what is it called? It's called cards, image classification, and then our training data. So this is going to be our data set. And now if we run a length on this data set, we will see it's 7,624. That's because that's how many images there are in this folder. If I take data set and I go 0, I see that I now have, you see the output of this is what we had talked about before. This is a tuple with the image and then the class. So this first value in the image is, first value in the tuple is the image. And the second one is the class. The class 0 is the ace of clubs. All right, so this also is an iterator. So we can do like 4 image class in, let's do image label in data set. And then we're iterating, when we do this, we're iterating over every item in this data set. So just to show this visually, let's do this. From TQDM notebook, import TQDM. And we're going to wrap this with TQDM so you can actually see it's iterating over this when we use a for loop on it. And we're returned back with the image and the label. Now that it's done going through the data set, you'll see it'll return the last image, which is the 2 of spades. And then that label for the last image is 52. There's 53 labels, index starting at 0. All right, so I'm going to cheat here a little bit and get our class labels. And we can do that pretty easily doing this. No, not doing that. We can do it like this. There's our data dir. I'm just making a dictionary here that maps with us the label number, because it's always going to have to be a number, to the name. So we could see that, in fact, if we look at this image, it's a 2 of spades. And if we look at the label, it's 52. Now we have a dictionary where we can look up this label and see it is a 2 of spades. Okay, so good. This image and label is coming through correctly. Now there's one last thing we need to make sure we do, And that's when we're returning this image. It's a PIL image. If you notice that, if I go to like dataset index location 10, this left side is a PIL image, and these are all different sizes. Well, none of them so far are anything but 224, so maybe they are all the same size, but let's pretend like they could be a bunch of different sizes. Pytorch model is going to need this to be all the same size. And like someone said in the chat, we do need to convert it to Pytorch tensors. So luckily we can, that's why we imported Torch Vision's transforms. And this allows us just to easily provide it some transforms that will resize it to 128 and then convert it to a tensor. So we can create this transform, and there's a lot more different transforms we could do, like changing the brightness and color and orientation and all that. But this chain is probably the simplest that we could create to, instead of returning that PIL image, now when we create our data set, if we also give it this transform, now we have a data set that returns tensors. So this first one is a tensor of shape 3 by 128 by 128. That's the height and width. So the shape of this is channels, height, width. And images are typically have 3 channels for red, green, and blue. I have a whole video on that on YouTube if you check that out. Are you guys following? Does this make sense? I see. Do you know what is the point of turning an image into a tensor so that we can change this, train a model on this data? So Pytorch needs to have a representation of this data in a tensor. It always needs to be a tensor. If it's audio, it's going to be a tensor of data points that creates a sound wave. Or often you transform the audio into like use a short form Fourier transform to get the frequencies. But with images, you need each pixel value and a number for each of these red, green, and blue that represent it. So no matter what your data is, video, audio, images, text even. Text, you tokenize it to make it into a numeric form that Pytorch can understand. What's my WPM? Not good enough. Wow, this is so neat. PLL straight to tensor. Yeah, it's pretty easy. Data, even if they are different sizes. What are you saying, Gabriel? How would you normalize the DT? Yeah, so normalization is kind of outside the scope of this, but yeah, that's part of what you might do is normalize the image so that all of the values are like subtracted by the mean and divided by the standard deviation, either by the image itself or by the whole data set. There's a bunch of different ways to do it. We're trying to keep this as simple as possible, not modifying the image other than transforming it to the same size and then creating a Pytorch tensor from it. All right, so that's step 1, data set. Step 2 is to create the model. All right, so the only other thing I will say is, oh yeah, we didn't talk about data loaders. All right, so a data set is how we just define the process to take one example from our data set. Now, the nice part about Pytorch is then we can just take that data set and then we've imported Dataloader already. I think I imported this wrong, by the way. Oh no, it is Dataloader. Yeah, so now we can take this data set and wrap it with a data loader. What data loader will do is handle parallelizing the process of pulling in this data set. What we'll find is that when you're training deep learning models, you want to do everything in batches. Because we know that the GPUs are really good at doing these large scale matrix multiplications and computations, we'd like to stack as many of these image examples on top of each other and feed them all to the model at once and then compute gradients and do back propagation, right? So data loaders make that really easy because then you can just take this data set and you wrap it with the data loader, and you can give it a lot of other parameters, but we're going to focus on two, and that's batch size. That's how many of those examples to pull each time you iterate over the data loader. And then also this shuffle. If you remember from before, all of our images were just, this data set is pulling it out by index in like the same order that the folders exist on the computer, which is not random. It's just every time we iterate over it, we're going to get all the label zeros and then all the label ones and twos. But when we're evaluating the model, that's fine. But when we're training the model, we want to have it get a bunch of different random labels in each batch. We don't want the whole batch to just be Queen of Diamonds or whatever. So that is what data loader lets us use by just putting shuffle into as to true. So if we iterate over if we iterate over, or instead of pass, I wanted to just do break. This data loader, it's an iterable too. It has a length also, I think. Yeah, so this length is actually, if we look at this batch size, it's just the length of our initial data set, which is 7624, with some repeating. I think that's one of the things you can set with it is, anyways, that's outside the scope of this, but it's basically 32 times, or the size of our data set divided by 32, because now we have batches of 32. If we look at our images shape now, it's a tensor, but now we have the shape of batch size then the channels, then height, width. And if we look at our labels, now instead of them just being numbers, we actually have a tensor, which is a one-dimensional tensor of 32 labels, which are associated with these 32 images. Does that make sense? The difference between machine learning and deep learning is roughly defined by depth. I don't know if I agree with that statement, JP. I think, deep learning usually involves training weights like in a neural network. Machine learning is more of a general term that I think encapsulates deep learning, but it can also include things like decision trees or gradient boosted trees or any other sort of like linear model. All that's kind of under machine learning to some extent because it's training a model on a bunch of data examples. It's not like modeling through heuristics. I don't know. Maybe that's semantics. Where's my other chat? You always hide here. You have structured data, which is usually tabular. What are you guys saying? You can certainly using it something like linear regression, but it's not necessary. Aren't we doing image classification? We are. Pytorch is used for unsupervised learning mainly. No, Hat Knight, that's incorrect. I love you, Hat Knight, but Pytorch is not necessarily, there's nothing that distinguishes unsupervised or supervised learning by using Pytorch or TensorFlow or LightGBM. So something being supervised, it's typically when you have a data set with a bunch of examples and then labels. That's exactly what we have here. We have a bunch of images and their labels. So this is a supervised task that we're training this model on. You have structured data, which is usually tabular, and unstructured, which is video, images, and text. No, I think you guys are getting it wrong. So like, just because it's images doesn't mean it's unstructured. You changed your name. I was wondering what the heck was in my feed. Yeah, I changed my name. I'm no longer Medallion Stallion on Twitch. Is there a way to pad with Pytorch transforms you want to transform without distortion? Yeah, so you can... Yeah. So that's the thing is there's so many, like anything you could think of, like padding a tensor to a certain size, or even doing like something like rolling a tensor across an axis, or all these things. There's usually some method that's already written to do that. So just like you asked, all right, I want to, instead of resizing by stretching, I want to resize by padding. You can do that using, usually a quick Google search and you have all that at your fingertips. If you have a label, you are basically supervised by these labels if you are using it. Yeah, this is a supervised task. There's very few applications, well, not very few, but a lot of what data scientists do in practice is supervised machine learning, where you have some labels on the data. All right, so we know about data sets, data loaders. Now let's create our model. We're going to cheat though a little bit. We're going to use a model. What is the most accurate regressor and classifier? In my opinion, it completely depends on the task that you're trying to work on. I guess I meant in practice, Pytorch would go for unsupervised learning. I don't know if I agree. Hi, how's it going? Okay, so let's create our Pytorch model, our Pytorch. We're going to cheat because we're going to import this library called Tim, which I don't apparently have installed here, but that's good because then I can install it and show you guys how. But it's a library that this guy who's really awesome named Ross Whiteman maintains, that has all the state-of-the-art image computer vision models in one place. And instead of reinventing the wheel, we're going to just install this library and use one of those architectures. So let me go over to here. I think it's because of my conda env list. Conda activate. There we go. Now I've activated it. And I can pip install Tim here. And what Tim lets us do once it's installed is we can take Tim and create a model, which is like just one of the great out of the box models for image classification is with EfficientNet. And we're going to use EfficientNet B0. B0 is just the size of the model. That's one of the smallest EfficientNet models. And we're going to say pre-trained equals true. And I probably spelt it wrong. Yeah, I did. So now it's going to download this base model from Tim. It'll only have to download the first time. It'll cache it locally otherwise. And now we have this EfficientNet backbone that we can use to build our model. But we're going to build a model the same way that you should if you're building it from scratch, which is by creating the same sort of paradigm as we did when we created the data set. So this time we're going to import Torch. We have imported Tim. We're going to import Torch. And then the Torch NN class, which is meant for building neural network layers. And we're going to start by, let's not do that base. We're not going to import our base model there. We're going to import it within our classifier class. So we're going to create a class called simple card classifier. And this is going to inherit from Pytorch's base NN module. Again, we're going to have to init. Let's give it a variable called number of classes. We know that to be 53, and that's going to be important because we're going to have to set the model shape of the output to be able to handle. And then we're going to take what we wrote here before, and we're going to make that our base model within this classifier. And we'll come back to this init. No, actually, let's just finish it. So we're also going to need to extract out the features from this model. Now, I don't want you guys to get too confused by this, but basically we're just going to pull off this last layer of the model, which is trained to do a classification task, and we're just going to pull out the features. And in this model type, the output size is 1280. It just happens to be that size in this model. So we need to then create a linear layer. I swear this is the most confusing part of the whole thing. That will go from that 1280 features out of that model to our 53 classes that we're trying to predict. Now we're done with the initializing of the model. So the models typically have this paradigm where you initialize all the different parts of the graph of the model, all the different layers, and then you have a forward method where you provided an example, and then this is what connects the layers. So here we define the layers of the model. And it's really all about the shapes. You need to make sure that the shape of this example that comes in, which will be our image. Do you remember the shape of those images? That this model can handle this input. and it's going to output what our label shape is, which is going to be just one tensor of 32. All right, so the way the forward is going to look is we're going to actually just take this input data, and we're going to start passing it through the layers that we defined above. Really, this base model is only we use it to pull out and create this features layer. So we're going to pass it through that features layer, and then we're going to pass it through our classifier, and then we're going to return that. Is that too much? How many columns and rows do you need for a model to be accurate? Are these legit questions? It really depends. Jeremy Howard's Fast AI is free, and I definitely recommend it. It's a Pytorch wrapper for anyone that doesn't know it. Yeah, Fast AI is nice. He does a really good job with those courses. Sometimes I wonder if it's a little bit too much on top of something that if you just learn this base idea of Pytorch underneath the hood, then you're not confined to exactly what Fast AI is set up to do. But Fast AI is great. Gabriel Keith is LOLing. Bye. Oh, I'm sorry. I didn't mean to be rude by asking if your questions were legit. But the columns and rows you need for a model to be accurate, that's like me saying, how many colors do you need for a painting to be beautiful? How many colors do you need? I don't know. That's not like something that's defined that you could ever define. Transfer learning. Yeah, so transfer learning. Thanks for mentioning that, because I kind of glazed over that. When we said pre-trained here equals true, that's because this efficient net that we're loading from Tim comes with model weights. And it comes with weights that have already been trained on the ImageNet dataset. And that's like a large dataset of a bunch of images and their labels. So it allows us to start training a model where it's already formed some sort of idea of what makes up different classes in that dataset. Like I think Apple is a class in that, and like different animals, and yeah, we can look up ImageNet classes. So there's 1,000 classes in the ImageNet. I think there's a second version of ImageNet, right? But you can kind of see what this base ImageNet has, like a forklift, type of fish, lemon. So the model, since it's already been trained on this data set, it already kind of has some understanding to how to make relationships between these pixels to detect things like edges and all that stuff. So it makes our training a lot easier. What project should I do as a data scientist fresher? Please give me a text reply. Kaggle. Just look on Kaggle and try to do a notebook that's on there. All right, so we have this classifier. And let's create a model from this. Can't assign. Oh, that's right. We also need to inherit. You just have to do this to inherit from itself. This line is just needed in the init. Try to name these all the same. Classifier. There we go. All right, now we have our model. it has all this stuff from EfficientNet. And then also we can kind of look at this last layer. Can I do layers? Kind of mix this up with how we do it with TensorFlow. But trust me, the last layer will output 53. It's going to have a shape of, the output shape of this is going to be batch size and then num of classes, because it's actually going to predict each class as its own. You could think of it like a column of predictions for each class. And the way I like to test this is by taking the model, and if we provide it in the images, it's going to test passing those images through the forward method. And then we do have an output, and it's important that it has this grad function so that we can perform back propagation on it. But the main thing is that we do have this output when we run everything, all of our images through the model that is of shape batch size and num classes. So we want to now train this model so that when we run this, and then we run a torch argmax, what argmax does, it'll find the column, you could think of it, where the highest value exists in the predictions. We want to train a model such that when we pass through our images, we'll get really close to our labels, which right now it's just random. I think this needs to be axis 1. Yeah. So right now it's just randomness, but if once we train it, it's going to look like the labels. You guys following? Facebook uses Pytorch to make llama. Yeah, Facebook, Meta actually created Pytorch, right? Torch was a base library, and they created Pytorch, which allows us to interact with it with Python. So it tapers those. Yes, that's a good question. So that linear layer, this linear layer takes it from 1280 to 53. Yeah. I wonder if there's like a visualization of a linear layer. Yeah, this isn't great visualization. I want to actually see with like all the weights connecting. But yeah, it's basically a way for us to take an input shape and say, convert this into the output shape. All right, so all right, this is the third and last step, which is actually training this model. It's getting exciting. We've done this almost from scratch. We've used a few little cheats like the Torch Vision import, and we did use Tim to help create our classifier. So I'm not really doing this from scratch, but we're going to train the model now by looping over those batches in our data loader, sending it through the model using the forward method, computing a loss, and then performing back propagation. Now, there's a bunch of videos that I'll go into, like you can watch online. 3 Blue, 1 Brown, I think, has a really good video on it where you can see it visually. But we're just going to actually do it and see how it works. So first thing we're going to do is create our data sets. We're going to actually create a train, a validation, and a test data set based on those folders that we downloaded. We're going to use the same transform as before, but we're using this, this data set that we created above. So everything else we should know. Now note here that we're shuffling the training data set, but we're keeping the validation and the test set not shuffled. Got it? Now we're going to write the main loop that almost every training loop that you'll use in Pytorch will have this. You need to provide the number of epochs. Epochs is considered to be a full iteration over the training data set. So we're going to actually have the model go over this training data set multiple epochs. And then let's store our training loss and our validation loss. Now our validation data set, our model is only going to see when it predicts, but our training data set, it's going to learn from. So the key here is that we want to keep our training data set separate from our validation data set so that our model, we can validate that our model is not only predicting well on these training examples, but it does well on our validation examples. Okay. All right, so let's create our model again with our simple card classifier. And then we're going to go for each epoch in our range num epochs. And then we're going to say, take this model. We need to make sure that we run this .train on it so that it is, the model is able to update the weights, because we do want the weights to change as it trains or else it wouldn't. Then for each epoch, we'll keep a track of the loss, and we'll start going through, iterating through the data in our training data loader. And this is batched with 32 images per batch. Maybe we could wrap this in TQDM so we can see it when it's training. Then we're going to take, I forgot. There's two things we need to define. I forgot. There's two things we need to define before we actually start doing this loop. We need to define our loss criteria and our optimizer. We need to import from Pytorch Optim. So I'm not going to go into too much detail about this, but we're going to be using cross entropy loss to compute the loss and how well each of these examples is predicted. And then we're going to use Atom, which is like the best optimizer to just start with off the bat. It's just, there are a bunch of different types of Atom, like souped up versions, rectified Atom and Atom W and all that stuff. But we're going to keep it pretty simple and just use Atom as our optimizer. And I'm going to put the learning rate. I'm just going to keep it consistent. We're keeping everything very simple here just because we're learning about how to train this model, not all the details. That's for later videos. All right, so let's take our optimizer and do 0 grad. We need to do this in the training loop. Then we're going to compute our outputs from our images. And then we're going to calculate our loss by taking this criterion, which will take in our outputs and labels. So this is going to compute using binary or cross entropy loss, the loss between the difference between the outputs and the labels. And then we can perform back propagation on this model. And we also need to make sure we step up our optimizer. Let's also increment this loss. We'll do it by the number of images in this data set. So this could also just be batch size. So this is just keeping track of how much loss we have through the epoch. It'll reset each epoch. And then we'll compute our total training loss as this running loss divided by the data loader size, and we'll append it. And then let's print off this training loss. All right, so I'm just gonna run this so you can see it is running. Now this is where I told you all we were gonna get into why running on a GPU is preferred. And this is exactly why. It's because it's super slow. It's a small model, relatively small data set. Is this from Pytorch? Yes, it is. And we're training it oh so slowly. So cool to see me do this on Twitch. I'm glad you're enjoying it. I wasn't sure if people would enjoy this. But this is where it's going to get really cool. Okay, not that cool, but see how slow that was training? It would take about 3 minutes per epoch to train. And it was training on my CPU. But we want this to run on the GPU. We want to leverage the fact that the GPU is so fast. And we showed you how to do that before. We did that earlier in the stream. And all we have to do is move our model to the GPU. And then we just need to do the same thing. Actually, we can do this. Instead of typing out CUDA, we can just automatically make sure that we have a CUDA device available and then set that to be our device that we're using it. And then we'll just put everything on the device. How much faster do you guys think it's going to be now? Any guesses? How difficult would this be to run on clusters on AWS or whatever cloud? On a single EC2 instance, not too hard. Once you start training on multiple GPUs, it's a little bit harder. 10 seconds per epoch, a few seconds. Okay, so this obviously depends on the size, the batch size that we're using. Hey, Rob, are you going to do any image augmentation? We're keeping it really easy here. We're not adding augmentation, but maybe in a future stream because that's important. But you guys think it'll be 10 times faster? I will say if the data, like the fact that we're doing everything so small might actually make the gains, make it less of a speed up than what we would see if our images were a lot bigger and our model was a lot bigger. That's when we're going to see the gains. But let's see how it works on GPU. Now keep in mind, we can go see on, here's my CPU run. It's still actually using a lot of CPU because it has to pull each of those images from disk, load it into the local RAM of the computer, and then load it to my GPU, where then it's filling up with 2.7 gigs. And I'm not sure if that's all just what we're doing here, but yeah, look how much faster it was. It ran in 23 seconds. So we went from 3 minutes to 23 seconds, and we're barely using the GPU memory because we could make that batch size a lot bigger. And there's a lot of tricks we could do. Like we don't need to necessarily load in all this data into or each time, we could do it a little bit more efficiently by caching this data into our local memory instead of loading it from disk every time we iterate over the data loader. But that's, that's just some additional stuff. Oh, I think this version of the model isn't training well. So we want this training loss to go down, right? We're going to track that. Let me make sure I'm... Yeah, so I actually think in order for this classifier to work, I ran into this problem before. In order for this classifier to work, we need to flatten this last layer to 1280 and then run the linear layer. So let's just double check. Oh yeah, this isn't working because this needs to go to device. Yeah. Let me just comment this stuff out. And see, now we have that newly defined model. It's gonna, our losses hopefully should start going down. And then while this is running, I'm also gonna add the validation portion of the loop. So while this is running through all of our training data in our training loader and computing our loss and then performing back propagation, we're gonna, right after that for each epoch, we're going to do the same thing on the validation data, but this time we're going to actually put the model in eval mode so that the weights are not updated, and we'll loop over them and only calculate the loss, and then we'll keep track of this validation loss. And then instead of just printing the training loss, we'll print the validation loss too. Okay, so the model's still not learning. Is that because I need to define my optimizer here? Is that why? See, this is the part of training Pytorch models which is hard to do live because it is a little bit of video. Your face white video helped me out a lot. Oh, I'm glad. Why Pytorch instead of TensorFlow? See, I'm one of those people that actually likes both. Yeah, so now it's learning. I think I just needed to define my optimizer using this model's parameters. I think the fact that I defined that above was the issue. But yeah, Pytorch is very, allows you to control everything because you're actually getting in here and creating this class for the model and then creating this forward method. You can do a lot of funky stuff. Like you can create the graph so that there are two models in parallel, and then you have a dense layer that connects them to, and like all this customization that you can do in the model, but also in the data loader makes it really powerful. And that's why people really love it. Pytorch is nice because you can kind of you don't have to do a lot of this creating the loop. You just create your model, you have your data set, and you can just say fit on this data, and it'll do all this stuff for you. But there are a lot of instances where having that control is worth it. It's worth writing a few extra lines of code. All right, what are Twitch people saying? Is there a reason why Pytorch does not have a fit method like TensorFlow? Yeah, I kind of just explained it. Like that's the whole paradigm of how it was created and the intentions behind. You're kind of in control of creating these objects and then running the back propagation on them on the tensors, which makes it a little bit harder to understand. But I actually think once you get over that hump of understanding why you're writing this training loop, it helps reinforce what you're trying to learn. Okay, so this is a good sign. We're training this model. The training loss is going down, but not only that, because our training loss can go down and that's a good thing. Our training loss can go down and it could be a bad thing if our validation loss is not also going down, because this is telling us that our model not only can identify those images, but it can generalize to new images that it hasn't seen before. So now we have a model that can classify images of cards. Want to test it out? Do you guys want to test it out? We probably would want to do a lot of things to make this perform better, but it actually works. That's all we were trying to achieve here. You would start with a learning rate, changing that. The number of epochs that we're training, we could change. We could test out a lot of things just out of the box and make it a lot better probably. But it classifies cards, and we're going to visually see that here. First, let's plot the losses. Yeah, let's import. So we can see here that our training loss and our validation loss is going down. I think this is right. Yeah, so they're both going down. Sometimes you'll have an epoch where things go up in validation set or training set if there's like a gradient explosion happens sometimes. But over the long run, you would hope that both of these are starting to go down. If validation loss stops improving, then you are at risk of being in the realm of overfitting. Pull down an image from Google to test it. Yeah, we could do that, Gabriel. But we don't even have to worry about pulling them down because we have that test data set that we haven't even touched yet. So we have a bunch of images we can test this on. Let's go ahead and try that out. So I have a bunch of stuff already written that'll make this a lot easier. Basically, I have... Okay, so I want this to be our test image. I have a function that will run that prediction and change it into a Numpy array. I have a function that will pre-process the image similar to what we did in our data set. And then this function just plots each of the predicted values, what those values are for that given card. You'll see here in a second. So I probably don't need to go in to too much detail. All right, so like if we go into this test data set, which the model hasn't seen at all, and we haven't even validated on using the validation data set. So five of spades, come on. It's not going to autocomplete. It's not going to autocomplete probably because of these spaces in the names. I hate spaces. Hate spaces. All right, so let's just do this. Let me go here. Into the test folder and to the 9 of clubs. Okay, so luckily they're just named like one JPEG and so on. Now I can remove these under spaces. No! There we go. Okay. So we fed in this 5 of clubs here through, and we're visualizing it, and we can see it's like 100% sure this is a 5 of clubs. And this is on images that we have not trained on, right? It's just it could be any image. We could pull it down from the internet. It should predict like this. So if we want to actually look at the probabilities, this is how they look when they come out. So if we look at this shape, it's a Pytorch. Is it Pytorch or is it converted to Numpy? Yeah, this is a Numpy array. So we did convert it to Numpy, but it's of shape 53 for each of these. And then we could run argmax on this. And we could see that the class that it's predicted is 8. And then we have that dictionary we created before. What was it called? Target to class. Target to class sounds like a 90s sitcom where kids need to get to class on time. Okay, prid class, 5 of clubs. So it's pretty obvious here that the highest predicted class is this 5 of clubs. But just to prove it to you, if we run this argmax on it, it's finding the location of the predicted class that's highest, and it's 5 of clubs. Let's just, for fun, loop through a whole bunch of these from glob and just see if we can find some that look bad. So this is going to be start.jpg. We're just using glob here to get a list of all of the images in the test data set. So test file names. And let's do a random choice of these file names, and let's take 50. So they're going to give us, if every time I run this, will give us random 50 images. So for each of these files, let's go ahead and run this. We'll run the processing on this file. Transforming, visualize it. Should we make it say the class? Yeah, let's actually update this code to say the predicted class. And we'll just do the same thing we did before. Argmax on these probabilities. And then we'll take our labels to class. What's it called? Image to class. The thing that I said was like a target to class, like a 90s sitcom. Pred. And then, so this will be in the title now. Let's just make sure this works. Predicted class 5 of club. So now it says it in the title. Yeah, whatever. I want to make it prettier, but this works. All right. You guys ready? Who's ready? Should I hit enter? Can I give a Streamlit advanced tutorial? I don't know Streamlit that well. Use Wave. Use H2O Wave. It's better. That's crazy. Even after starting to study machine learning, this blows my mind. Yeah, pretty cool. All right. If you guys want me to hit enter on this, I need you to type F in chat. Just put a big F. Anyone? Okay, we got a few people. I don't know. Maybe not enough for me to hit enter. No, it's not enough. I'm just going to end the stream now. No one from YouTube. Oh, we got first time chatters here? Now people are trying to say it. Why tease me? I just want to make sure people care. Okay, so one person, Gabriel from... There we go. Drum roll, please. So to do this properly, we probably should on the whole validation set, compute stuff like accuracy. Again, I'm trying to keep this super simple, but I see you guys do want to see what the output looks like. So we're just going to scroll through some of these and see if any of them are predicted wrong. Queen of diamonds. All right, we're 2 for 2. 9 of spades. Okay, so it had a little bit of an issue distinguishing between clubs and spades on this one. Knew that one. Knew that one. Just tell me if you see anything. 5 of spades. 7 of diamonds. Man. Oh, it really doesn't like that big heart. Thinks it might be a 9. Wait, what is this? What is this in the data set? Oh, geez. I did not put that there. That is pretty funny, though. It's very apt for what's going on right now in our politics. Okay, Jack of Hearts. Is this right? Yes. Do we see any that are wrong? This one is bizarre, but it still got that 2 of spades. Probably was able to find it in the corner. King of Hearts. Yeah, this one has like... Okay, so it did get this one wrong. So our classifier is not perfect. It's not perfect. This is a 5 of clubs. We can tell this is a 5 of clubs. It was a little confused and thought it was a queen of clubs, but you could kind of see why. Like most of these cards don't have that much on them for number cards. It's a completely different background color. I mean, I'm making excuses for my model, but it's good that we see one that's not correct so that we know it's not just, I'm not just faking it here. All right. So pretty cool. What did we learn today? Is this right? 2 of hearts. Yes. So we learned that the 3 main paradigms in Pytorch when you're training your model is you need to be comfortable with creating these data sets so that you can then wrap them in the data loader. Then you define your model. Your model will have this init method where you define the parts of the model, and then your forward method where you'll actually define how the data will flow through these parts. And then this training loop. Before you define your training loop, you need to have decided on a loss function and your optimizer. But once you have that, you can actually just make this part of the loop, which will train your model. We can also validate on some validation data while we're training. And that's it. Now we have a trained model. Now let's say we did want to save this model. The way you typically do it is, there are a few ways to do it. You can just save the weights. Think like this. Okay, so I need to remember torch. Oh yeah. So sorry. So in Pytorch, you have your model, and then you have your state dictionary, which actually contains all of the weights that we trained in this model. And then we can take torch and save these weights to disk. And then later on, we could, as long as we load in this model defined the same way, we could load in those weights and predict. Can you pickle it? Yeah, I think you could pickle it too. You can sleep peacefully in SA. Nice. What's SA? South America? South Africa? Rob, Keras would be equivalent. In Keras, what would be equivalent to this? So efficient net, you could get this exact same efficient net in Keras very easily. Because these architectures are so powerful and so like widely used, Keras, TensorFlow Keras has the same thing. So the actual architecture of the model is going to be identical because all Keras, all TensorFlow, PyTorch, whatever you're using is doing in the back end is the same math and it's the same building blocks. It's just a different interface of working with them in a different library that you're using. But the architecture really doesn't care about what you're using to train it, right? You can actually convert this to like Onyx format, which will let you run it universally. Can you explain how does transfer learning work? Yeah, we talked about that a little bit at the beginning, but we talked a little bit about ImageNet and how we were using a model that was pre-trained on ImageNet classes. So what you can think of this as this model, if we had just, let's do it. So if we just do this training of this model, we'd actually have to define pre-trained here. We could do this exact same loop on a model that is not pre-trained. So we just have to set pre-trained defaults now. And now we're training that exact same model, but the weights of the model are just initialized as 0 or 0.5 or whatever they initialize as. There are different ways to initialize them too. But that means that we're not getting the benefit of having weights that have been trained on even a separate task. So look at these losses. We're starting at 3.2 and 2.4. In our other model, when we were training it to start off, we were at 1.5 and 0.45. So right out of the gate, the model already has transferred some of its knowledge about training on these ImageNet images and been able to apply it to predicting these type of cards better. Now, there are situations where you might want to not use pre-trained weights, but most of the time it doesn't hurt because if anything, you're just going to wipe out what the model had learned about those pre-trained weights by more training on your new data set. So yeah, in reality, you might be able to get a similarly performing model without using pre-trained weights. It's just going to take you a lot longer to train. So when you think about this stuff like the language models that we use, transfer learning is huge because you can use a model that's already been trained on the entire internet. I'll try to adapt the recognition of chess positions from screen chessboard captures. Yeah, that would be a great application of this. And I know that there exists some models out there that we've used before on stream that can just take the chess.com or any of those chess board setups and figure out the PGN of that position based on classification like that. But there's an extra step of identifying all the different squares and then running a separate classification for each, but you guys get the idea. All right. Sorry that the Twitch chat didn't show up here all night. I meant for it to. I don't know what happened. There are different bars, the confidence of the epoch iteration. The bars, I know that Kappa asked this question a while ago, but the bars in that graph were showing for each of the classes, each of the types of cards, which one did it think was the type that the image was? Could you give us access to the notebook? I'll do you one better. So I have a video coming out that's going to be a very condensed version of what we went through today. I've already recorded it, and there's going to be a Kaggle notebook that I'll release with it. The Kaggle notebook you'll just be able to copy with the data set, run from the start to the end, and ask me questions. Does that sound good? Ignored? Trish Trap being treated like the middle child. Hey, I was a middle child, so I feel for you. What else are you saying? Side note. Have you worked with Kudif and KuPy? Losing my mind trying to get it installed on Windows. I think I need more Docker container. Yeah. I've had issues with getting it installed. But once you do, especially with what's coming out soon, and I wish I could talk about it, but I'm not allowed to. May have signed an NDA about it, but there's going to be some cool stuff coming out. So be on the lookout, people. Kudif. I also want to mention H2O World. If you are in the Bay Area, or even if you're not, and you want to come to Gen AI World, I believe I'll be at this conference. It's going to be great. We'd love to have you there. Check this out. I'm going to post this on my socials, but make sure that you check this out and join us if you can. I think it's also going to be streamed. So this will be very cool. Coming up in just about a month. So things creep up on us. All right. Thanks everyone for hanging out. Let's find a channel to raid on Twitch. That's always a fun thing to do. Was it hard for you guys on Twitch to find me now that my name has changed? Hopefully it wasn't too hard. Nick Wan is streaming. He's doing data science for sports. Okay, let's raid Nick. Nick Wan, the man. All right, I'm going to do... How do I get here? Let's raid. All right. All of you who are following on Twitch will be sent to Nick's stream. Get ready for some awesome data science stuff. And then those of you on YouTube, I'll see you next time. Thanks for joining me. Look out for that new